Alright, so in this video we are going to discuss hypothesis testing. Hypothesis testing is a process to verify, just like its name tells us, to test hypothesis, which is a standard process that is used in a wide range of branches of any kind of science, not just like in statistics, as a general mathematics, as a general mathematics class, or like in engineering, even in chemistry, biology, but it's also widely used in the medical field as well, in the psychiatry and psychology as well. So you'll see later how many application, how wide and how powerful this process is to prove something right or prove something wrong. Essentially, having enough statistical evidence to prove something wrong or not, or failing to prove something wrong. So you'll see the process as we go along. Well, number one, let's go over some definitions. Hypothesis. What is a hypothesis? It's a claim or a statement about a property of a population, and the hypothesis test, or sometimes you call it test of significance, is the actual procedure of testing that claim of a property of that population. And what can we cover as the property of a population? Well, we can test a claim about proportion. We can test a claim about some kind of mean, or even what else? Standard deviation or variance. Okay, and this will rely on the different distributions that we have covered so far. So like in last chapter, in interval confidence intervals, we actually applied the normal distribution, and from there we use something called the t distribution, which is the student's t distribution. All right, so we're gonna bring this back here as basically the major tool to go over this hypothesis testing. Okay, so what is a hypothesis again? Well, it's a statement that may or may not be true. May or may not be true. That'll depend on the statistical evidence that we are able to gather in the experiment, and given the data, for example. Okay, so in this case, we are going to make decisions. Is this true? Is this false? Based on statistical processes, not just by saying, well, the number is bigger, so yes, that's going to prove wrong or whatever. All right, just roughly speaking, well, that's not enough evidence, So, for example, what else? Well, before going over examples, so let's look at the composition or the structure of this type of processes. Well, every hypothesis has essentially two hypotheses. Number one, the null hypothesis, and the alternative hypothesis. All right. How can we, make a distinction of them? Well, this is the one by default. Okay, by default. And the alternative hypothesis, which is the researchers hypothesis, right? Now, well, what about which one is which? Well, let me give you an example. Consider, for example, the the American justice system. Okay, so if every time a criminal is going to be judged in court, by default, which is the null hypothesis, it's going to be that the criminal is innocent unless otherwise the prosecutors have enough evidence, if they have enough evidence, sufficient evidence to prove this wrong, right? In some cases, well, there's evidence that to prove that the criminal is indeed a criminal, is guilty, or otherwise the prosecutors fail to prove this criminal guilty and is set free. So that's pretty much what we are going to use. But now, well, in this case, well, we have a criminal. Well, the prosecutor is going to look for fingerprints. It's going to be for I don't know, remains of blood, sweat, or some hair, or weapons, anything that can incriminate the the criminal, and that's going to be enough evidence to otherwise, instead of having this criminal an innocent man, well, it's going to be a guilty man and it's going to go to jail. Okay, well, in our case, in statistics, how are we going to do that? Well, we are going to gather data, and then from the data, well, we are going to make some statistical processes and then compare with some standard values, just the same way. Well, what about the comparison with standard values in the criminal example? Well, the standard values is the law. For example, is it okay to carry, fancy weapons? Is it okay to kill a person? Well, no, according to the law, that's not right. So that's going to be enough evidence, well, to call this a criminal. Well, in this case, we're going to use the normal distribution. We're going to use numbers that, in a way, are going to look compelling. And even if they are compelling enough, we may even fail to reject the null hypothesis. How many times have you seen, a criminal that everybody knows is a criminal and he's let go as an innocent man, and that's because they don't have enough evidence to prove. I mean, even if people saw him killing whatever man or whatever person, well, there's not enough evidence, so he's not guilty and he's left and he's set free. So we are going to run into these situations here when we do this hypothesis testing. Okay. All right. So let's describe these two hypotheses real quick. Well, the null hypothesis, which is denoted HO or HO, right? No, not that one. HO. HO. And the alternative hypothesis denoted H1. So also this is HA for alternative. So, well, if you read other books or if you watch other YouTube videos or other alternative or other online resources, typically, a mnemonic to memorize this is to have a ho and a ha. So that's the two essential, this essential elements of the hypothesis testing, ho and ha. Null hypothesis, alternative hypothesis, which is the null hypothesis is the one that is believed to be true unless there is overwhelming evidence on the contrary. We have a criminal that is, well, by default, he's innocent and unless proved otherwise with evidence. So that's what we are going to do. So the alternative hypothesis will always state that the mean of the population is less than or greater than or maybe not equal to some specific value that is by default set. All right. It is also known as the research hypothesis because that's going to be the one that will state the position as a researcher, or in this case, the position as a prosecutor to determine whether the criminal is going to be it's going to be guilty. Okay. All right, so let's look at some examples. Let's look at some examples to determine. Hold on, give me a second here. Let's see. I think I need to erase something here. Just. I forgot to erase this from my notes. Otherwise, it's not going to make too much sense. All right. So as our first example, stating the null and the alternative hypothesis for the different situations that we have in here. All right. So let's state them, and we are going to actually describe or discuss a couple of very important points when it comes to stating this, because this is sometimes one of the trickiest part. It's the very first step to conduct a hypothesis testing, but when it comes to actually put the data together, well, it could be a little bit tricksome at when interpreting and when reading our situation, when reading our word problems, and see how we are going to digest the information. So let's look at this. All right, so we have that a light bulb manufacturer has developed a new light bulb that it claims that has an average life of more than 1,000 hours. All right, more than 1,000. This is the key word: more than, less than, or equal to. Okay, so state the null hypothesis, and the alternative hypothesis. All right. So in this case, we are be careful with the symbols that we are going to use. Notice average. Average is a synonym of mean. Okay, so we are going to write the ho and the ha. Ho is null hypothesis. Ha is the alternative hypothesis. Okay, well, keep in mind that as we mentioned on the previous page, the alternative hypothesis is the one from the researcher or the manufacturer, or the one that is conducting something, that is coming up with something. Okay, and in this case, it's going to be the alternative hypothesis is that the average life of these light bulbs is more than 1,000 hours. All right. What is going to be the null hypothesis? Well, the null hypothesis is going to be the logical opposite of this. Okay. Before doing this, let me do a mini review of logical opposites. So how are we going to work with those? Well, let me just get a piece of scratch paper here. Okay. Logical opposites. I don't know if opposites go with double P, whatever. Okay, what is the logical opposite of x greater than 3? So for the opposite of x greater than 3, it's going to be x less than or equal to 3. You can think of this as the complement, if you will, but we are not going to call it a complement in this case because we are using our reasoning. We are going to call it logical opposite. What is the otherwise? As another example, z less than or equal 1/2. What is the logical opposite? Well, that's going to be z equal, or actually greater than 1/2. And last but not least, let me make up something else. What is the opposite, the logical opposite of, I don't know, x equals 5? And be careful with this one. This might be the trickiest of them. Okay, so the logical opposite of x equals 5 is x not equal to 5. All right, going back to hypothesis testing, hopefully this helped here. So the logical opposite of mu greater than 1,000 hours will be mu less than or equal 1,000 hours. All right, and now just to jump a little bit ahead of the game, so because of the direction, it's going in this direction is greater than, when we do our testing, this is going to be a right-tailed test. So if you look at this, well, what do you mean by right-tailed test? Well, you'll see. For now, let me just give you the picture, and everything will make more sense as we move on through this chapter. Let's look at another example. So a pizza delivery company claims that its average delivery time is less than 45 minutes. All right. So I'm going to highlight the sentence that is going to give us the alternative hypothesis, that is the ha. Okay, so let's state ho and the ha. So less than 45 minutes. Okay, less than 45 minutes. So the mean or the average time is less than 45 minutes. Okay, and I forgot to raise the answer to the previous. I think you already saw it. I'm going to raise, pretend you didn't see anything. Yep, too many spoilers here. And well, for the null hypothesis of the situation of the pizza delivery guy will be greater than 45. Well, what would be the situation? For example, let's say that I don't know, these Gallup polls, that typically give reviews of restaurants, and for example, maybe one of the categories is the delivery time of different pizza places. Well, so for some reason, well, a few customers complain about the pizza place. Well, the pizza is really good and I like it. However, they take too long. They take more than an hour, 2 hours. So the Gallup poll is going to take data and then they're going to record them in their database, and that's what they're going to say. That's going to be the default. Whatever they're judging you or judging the pizza place into, that they take too long. But then you guys, as a pizza deliverers, well, then you say, no, that's not true. My pizzas are delivered within 45 minutes, right? And that's your alternative hypothesis. That's what you want to prove, right? What you want to prove, and not the null hypothesis. Okay, then we have another example. Oh, by the way, look at the direction of the inequality sign. Now it's going in the negative direction. So if we have a bell curve, in this case, this will be a left-tailed test. Okay, again, if this doesn't make too much sense for now, you will see it actually the next page will be to describe what a left tail test is and what a right tail is, and actually a two-tailed test is. So now we have another example. So we have a cereal manufacturer uses a filling process designed to add 18 ounces of cereal to each box. Okay, so in this case, well, this is the researcher or the manufacturer. This is what they claim they do. This is what they want to prove. Somehow, well, someone else has said, no, that's not true. Your cereal boxes do not contain 18 ounces. Well, notice in this case it doesn't say more than 18 or less than 18. It just say flat 18. Plain vanilla 18. Alright, so let's state the ho, the ha. Okay, the null hypothesis, the alternative hypothesis. Well, so in this case, the mean or the average amount of ounces of cereal in each box is 18. Okay, well, what is the logical opposite of something that is equal? Well, never mind about. Actually, this is the one that is not equal, the alternative hypothesis. Never mind. Okay, so it's changed, and I will tell you why. I'll tell you why in a minute. Sorry for the confusion. Notice this, not equal. How is this going to look like? Well, when we conduct the test, this is going to be a two-tailed. Two-tailed test. Okay. Now, something very, very important that you might want to keep in mind. I would like you to observe something. Look at the inequality symbols for the has, for the alternative hypothesis. Notice, and let me write that as a note over here on the top of the page. The alternative hypothesis never has the equal logical symbol. Right? It is only the null hypothesis that has it. Less than or equal, greater than or equal, equal. See, no, none of the alternative hypothesis have the equal. This is not equal, doesn't include equal. This is just less than, does not include the equal. This is greater than, does not include the equal. So that's very important when stating the null hypothesis and the alternative hypothesis. That is the ho and the ha. Only the ho has the equal. The ha never has the equal. All right, write it down on the top of this page. That's something you want to keep in mind. Now let's look at different types of testing. So let's look at two-tailed hypothesis test. All right, so when are we going to use a two-tailed test? That's going to be used when the alternative hypothesis is expressed as not equal to a specific value. And you can look at the example on the previous page, the one with the cereal boxes. That one is not equal to 18. Okay, so how are we going to do? Well, I already gave you the pictures, right? So we're going to use the normal distribution. Of course, later on in preceding chapters, we are going to introduce other distributions that actually are not going to be symmetric. You'll see later on. For now, we're going to focus on the normal distribution. So we are going to draw the bell shape of the graph. We're going to put in the middle the claimed value, the one that we want to test wrong. All right. And then we are going to split our significance level. Oh, where have we heard that before? Significance level. Remember alpha from the previous chapter from confidence intervals? Well, that's coming back. All right. So, and in this case, we are going to split, and we are going to have two shaded regions. I'm going to explain later what about this. Shaded regions, essentially, when we gather our statistical evidence, we are going to convert everything to standard values. Well, what are those standard values? Those standard values are called z-scores or t-scores, depending on the type of distribution that we use. And you will see a lot of resemblances between the calculator functions and the statistical process that we're going to do in this hypothesis testing and the previous chapter, which is confidence intervals. However, we are going to use this data to test for significance, which as you will see in the examples. So we are going to gather some evidence. We are going to convert that to a z-score. If our statistical data falls in the non-shaded region, then we do not reject the null hypothesis, which means that we do not have enough evidence to to support our claim. So we need to gather better evidence. Otherwise, if our statistical value falls in either of the shaded regions, well, then we're good to go. Then we win. Then we as researchers win. We have enough evidence and we win the argument. Okay? So what is the essential process? Well, to conduct a two-tailed hypothesis test. Collect a sample of size n and calculate the test statistics. In this case, well, it could be a sample mean or a sample proportion. Well, in this case, for the serial boxes, well, we are going to we are going to call the sample mean. We're going to plot the sample mean on the x-axis of the sample distribution curve, which is here. Okay. Now, again, as I mentioned before, if the sample mean lies within the unshaded, well, we do not reject the whole. Otherwise, that's going to be we do not have enough evidence to support H1 or HA, the ha, all right, which is the alternative hypothesis, so we lose. Otherwise, if the sample mean lies within either of the shaded regions, well, then we reject the ho and we support the ha, and we win the argument. Okay, so that's why we call this the two-tailed, because we are shading both of the tails. All right, let's look at the next example, at the next type of one-tailed hypothesis testing, and that's used when the alternative hypothesis is expressed as greater than or less than a specific value, like the example of the pizza delivery or the light bulb, the ones that we did earlier in the previous few pages. So in this case, like I mentioned before, so depending on the orientation of our logical sentence, greater than, it's going to be right-tailed. The pizza delivery example, well, it's less than, it's going to be left-tailed, like this one. And again, the process to determine whether we have enough evidence, it's the same. Collect a sample, and collect a sample, calculate the test statistic, and if our test statistic lies within the non-shaded region, then we do not reject the HO. Okay, so we lose the argument. We do not have enough evidence to support our claims. Otherwise, if our statistic value falls within the rejection region, well, then we have enough evidence to support our claim. Okay, and we reject the null hypothesis, and the alternative hypothesis wins. Okay. So let's look at some examples. So we are going to do our first type of exercises. Well, in this case, we are going to test a claim about a population proportion. All right. So testing the claim. So these are some assumptions that we need to consider before we can conduct hypothesis testing. In which we test a claim about a population proportion. So the sample observation, that's going to be our simple random sample. That means all samples are equally likely to be chosen. That's if you want to review those definitions, those are from our very first chapter. And then the conditions for the binomial distribution are satisfied. That is, there's a fixed number of independent trials having constant probabilities, and the outcomes are two, which is either success or failure. Remember, you might remember the binomial distribution, in which, well, we toss a coin, we get heads or tails. We have a test, an exam, we either get the question right or we get it wrong, and whatever next trial is not being affected by whatever we do on the previous trial. So that is, they are independent trials. And then the product NP and NQ has to be greater than or equal to 5. Well, in this case, N is the sample size, P is the probability of success, and N, again, here is the sample size, and Q is the probability of failure. So we multiply the sample size by the probabilities, and if we get something greater than or equal to 5, then we're good to go. Okay, so notation. What are we going to have for notation? Well, N is the sample size. P with a hat, well, here is a little bit hard to see. Well, maybe it's easier to see it in your papers if you have them. Let me get my pen here. Where did I put my pen? Okay, this is a P with a hat. That's going to be X divided by N, which is the sample proportion. You will see about this X and N. P is the population proportion, P without the hat, which is the one in the null hypothesis. Okay, so we need to be very, very careful here with all the symbols that we are going to be using, because we're going to have a P with a hat and a P without a hat. The one without the hat is the one that is stated in the null hypothesis, that is in the HO. All right, and Q is as usual the complement of P, 1 minus P. All right. Okay, so there are two different methods to test a claim. Number one, using the C-score and the p-value. Okay, so how are we going to do that? Well, so we are going to reject. We're going to use this formula: p hat minus p divided by the square root of this big number pq over n. It's going to be kind of an ugly looking formula, but it's well, in practice, well, it's only calculator that we are going to be using mostly, you know. And well, this is method 1, and method 2 using the p-value. Okay, so in this case, using using the probability for whatever we're claiming it's big enough or significantly enough or maybe not enough. And what is the criteria? So we are going to reject the null hypothesis. That is, we win the argument if our p-value is smaller than or equal to the significance level, which could be 5%, 5% significance or 1% significance. We want to be more precise. But in this case, we lose the argument. We fail to reject if our p-value is way larger than alpha, which is the significance level. So what about the significance level? Well, the lower the significance level, it's we need to make our our sampling or our survey with more precision, because the smaller alpha is the highest standard that we need to take care of when conducting our research. Because for example, if let's say that well, I think the examples will be, once we do the examples, this is going to make more sense. And well, right now it's just formulas, and here is p-value, alpha. Well, how about we do an example? Okay, so this is our first example, example 1. Well, so let's look at the situation, let's read it, and then we are going to get all the information. Well, someone at the government claims that that more than 50% of the U.S. tax returns were filed electronically last year. A random sample of 150 tax returns for last year contained 86 that were filed electronically. Test the claim at alpha equals 0.05 significance level by comparing the calculated z-score to the critical z-score, and by comparing the p-value to the significance level. Alright, so a lot of numbers here and there. Well, I'm going to show you the picture one step at a time, So this box right here is going to be very similar to what we did in this previous chapter with confidence intervals. From here, we are going to get the information for the population, in which, well, the population size, well, even though that's a data that can we obtain online or something, we don't know. Well, let's say we don't have access to that information. Well, P, which is the probability of success, and then Q, which is the probability of failure. Well, in this case, that's going to be obtained from the original claim, 50%. But well, that 50% should be converted to decimal. 0.50, 0.50, which is also the complement. So this is all the population. What are we going to do? Well, take a sample and gather evidence, gather the evidence to prove that this is maybe wrong or maybe right. Well, we'll see. So we're going to take a sample of n, this is going to be n equals, take the sample, okay, n equals 150, for which 86 were successfully, successes over the total in the sample, so x equals 86, okay, and then p hat will be the quantity, as we stated in the previous page, the number of successes over the sample size. Successes in the sample over the sample size. That is 150 divided, oh, I mean, not 150, otherwise it's going to be too big. So where's my YPad? Whoa. Give me a second here. Oh, here it is. So this is going to be 86 divided by 150. And that's going to give us, using a calculator, 86 over 150, I get 0.573. What is Q hat going to be? Well, Q hat, well, will be the, well, actually we don't need Q hat, never mind. We can erase Q hat. All we care about is P hat and Q hat. Okay, so this is going to be our sample, okay, with this data. So population sample, okay. Now let's do a few highlights here. This alpha equals 0.05. This is significance level of 5%. That is, this alpha equals 0.05. It's either going to go to one side, to the other, or split in two. How are we going to know? Well, we're going to know that when we state the null hypothesis and the alternative hypothesis. So, because this is alpha significance level 5%, this is going to be 95%. You know, the unshaded region will be 95%. All right? So, what are we going to do here? So, first of all, let's actually state HO-HA or HO or H1. Well, different books say use the letter A as the alternative. Other books use the number 1 as the alternative. We're going to use the letter A as a subscript. Alright, so what is the research claiming? Well, the research is claiming that the proportion of the population that filed their taxes electronically, let's see, let's highlight, claims that more than 50%. Notice it doesn't say more than or equal, you know, more than. That's how we know that's the alternative hypothesis. So in this case, 0.50. What is the logical opposite, which is going to be the null hypothesis that less than or equals 0.50. All right. Now, look at the direction of this. Look at the direction. Okay. The direction, it's pointing towards the positive side. So what are we going to do here? Well, this is going to be a right-tailed test. Okay, so let me shade the right tail. All right, and this little bar will be a limit value, will be a bound. You know, actually, this will be the z critical, okay, which will be something. How are we going to get that z critical? The same way as we did it using when doing what was that? Confidence intervals. So let's calculate that critical value. We get that by using our calculator, using the inv norm of, in this case, well, if we read the graph from, well, basically from negative infinity to positive infinity, but in a more, you know, in our percentage point of view, from 0 to 100, this is going to be the number, the 95 percentile. Okay, so we are going to find the z-score of the 95th percentile. In other words, we are going to find inv norm of 0.95. And well, in this case, in your calculator, you may have other numbers here. Just do the inv norm 0.95 and erase everything. So I'm going to show you how to do it on the calculator. So we go. Second dister for the distribution, and we're going to type inv norm. So which portion of area do we want? Well, in this case, 0.95. And this 0 and this 1, just keep it. Don't change anything. Keep the 0 and the 1. So if you want to keep them, that's fine. Otherwise, if you want to delete, let me show you that nothing happens if you delete the 1, the comma, the 0, and the other comma. Either way, you should get the same. Alright, now another thing to recall is that the rounding rule for z-scores is 2 decimal places. Okay, so this is the z-critical. So let's see. Z-critical 1.64. Okay. Now, this is going to be the unshaded region. So in this case, in this region, we fail to reject the null hypothesis. Okay. Otherwise, in this region, in the shaded region, reject the null hypothesis. And in this case, we win. That means we have enough evidence. Well, how do we know this? Well, let's do the calculations. Let's calculate the test statistic. And let me write down the formula, the one that I showed you on the previous page. So the formula to calculate the test statistic is z equals p hat minus p divided by the square root of pq divided by n. All right, so let's write down numbers. P hat, that's the from our sample. Okay, let's recall that this comes from the sample. And this guy comes from the population. And by the way, I didn't write this equal 1.64. Well, I had it over here. Okay, had it over here. So let's put numbers. The p hat is the one that we calculated from our sample. The number of successes over the sample size, the number of successes of the tax returns that were filed electronically. Okay, 0.573. So this is 0.573 minus p from the population. Well, that's 0.50 divided by the square root of pq. This pq, these two come from the population. 0.50, 0.50. 0.50 times itself, and divided by n, which is the sample size, which for us in this case is 150. Using a graphing calculator, you should get 1.79. Okay, let me show you the syntaxes here in case you have trouble getting these values. Well, first of all, I'm going to open parentheses. I'm going to subtract, I'm going to type the subtraction 0.573 minus 0.5 or 0.50, doesn't matter, close parentheses. to make sure that the division affects both the two quantities in the numerator, I'm going to divide by the square root, and in this case 0.5 times itself, and divide by 150. Boom, what do we get? 1.7088 blah blah blah. But again, we're talking about z-score, so the rounding rule for z-scores is 2 decimal places, so that's why I will have 1.79. all right, so we get 179. That's our test statistics. So now this 179, let me go up here. So the critical value, the critical value is 1.64. Where is this 1.79? In this case, well, 1.79 is a number that is greater than 1.64. That is our z-statistic of 1.79. All right. Well, so in this case, because our test statistic fell in the shaded region, what is our conclusion? Reject the null hypothesis. So we have enough evidence to claim that more than 50% of the U.S. tax return will file electronically. So this is going to be our conclusion. Well, we reject the null hypothesis. There is enough evidence to support it. All right. Now, how are we going to do the test? That's the second method, because again, this is method 1 using the test statistic, the z-scores. Method 2 will be calculating the p-values and compare with the significance level, which in this case is 0.05. All right. So how do we compute the p-value? All right. So in this case, we're going to find the probability of having this z-score. Well, we're going to use the command normal CDF, and we're going to type 1.79, comma, big number, and then 0 and 1, okay, which is the default values here. Well, so in other words, we're finding the area between 1.79 and whatever number. So we are computing this area, if you will. Okay, so how do we do this in the calculator? Well, let's go to second dister for distribution, normal CDF. The z-score that we got, that's our lower, 1.79. The upper, which is big number, I'm just going to type a bunch of 9s. And then let me keep the 0 and the 1. And then I'm going to paste. Okay, I'm going to have this. And I'm going to get 0.0367. That is 0.037. Okay, let me check something out real quick. What if I delete the 0 and the 1? Do I get the same? Yes, I get the same. Okay, so you may not need this 0 and this 1. All right, what is this p-value? Okay, so that equals p. So in this case, let me write down the p-value, which is, and put it next to alpha. So in this case, 0.0367 0.7 versus 0.05. Okay, which one is bigger? Well, in this case, alpha is bigger, or p-value is less than alpha. Well, under the criteria, let me go back here. What if our p-value is less than or equal? Actually, let me put that less than or equal, less than or equal. So we reject the null hypothesis. All right. So the two ways, whether you do it using method 2 with the p-values or using the test statistics by z-scores, both answers should check. For example, if you have a z-score that rejects the null hypothesis, well, you cannot get a p-value that actually failed to reject. Maybe in that case, double check all your calculations. So both methods should check. So that's our first example. Let's look at another example. So, nationwide polls claim that the President of the United States has less than 64% approval rating. In a random sample of 125 people, 74 of them gave the President a positive approval rating. Test the claim at alpha 0.02 significance level by comparing the z-score to the critical z-score and by comparing the p-value to the level of significance. All right, so first of all, let's see what about our sample, what about our population? Well, the size of the population first. Well, so N, big N, that's the population size. We don't know and we don't care. Okay, that's the proportion that gave a positive rate, you know, that its claim is 64%, that is 0.64, and Q, which is the complement of it, 0.36. All right, that's the complement of 0.64. What are we going to do? Again, take a sample of N equals 125, for which X equals 74 gave the President a positive approval rating. All right, and let's find the p hat, that is the sample proportion, p hat, which is 74 divided by 125. That's going to give me 0.5592. Which in this case, well, it's less, right? I mean, 0.592 is less than that. So maybe you could say, well, I get 59.2%. Well, so yes, that's less than 64%. However, you will be surprised at what's going to happen here. Yes, you may think you have enough evidence, but may not be true, and you will see. I don't want to spoil this, but something weird is going to happen. Something rather interesting, not weird. All right, so our alpha here is 0.02. That is 2%, right? That means 2% significance. That is, the unshaded region will be 98%, you know, 98%. And then in this case, well, one thing to notice, first of all, let's take the ho and the ha. Let's highlight. Let's highlight whatever we need. In this case, less than 64%. Less than. So that's our ha. That's the proportion of people is claimed to be less than 0.64. So the null hypothesis, HO or a HO, is going to be the logical opposite of this statement right here, which is p greater than or equal 0.64. Okay? Hopefully so far so good. Well, what else are we going to do here? Well, so look at the direction of the ha. Notice it's boom, going to the left. That means we're going to have a left-tailed test. We're going to perform a left-tailed test. So in this case, this alpha is going to go over here. Okay, as it is. All right. Do we need to find? Do we need to know and to do anything else? Well, not really. So shader region, reject the HO, the null hypothesis. Otherwise, fail to reject the null hypothesis. So notice the wording we are using. We never say accept the null hypothesis. We say we fail to reject. We do not accept, because that's what we want to reject. We don't want to say. It's not the same. The wording matters here, you know. So this is the picture. Let's get the numbers now. All right. Notice in this case, if you scan or you read the graph from 0 to 100, this is the second percentile. Okay, so how are we going to calculate the critical value? Well, Z critical will be inv norm, that is the z-score, related to the second percentile, that is 0.02. And I'm just going to write the 0 and the 1 if you will. That's fine. Again, we don't need those. That's enough. That's okay. Okay, so let me go back in here. The good thing about this calculator, I don't have to go everything there. 0.95. Instead, I'm going to write 0.02. And I get negative 2.05. Well, the rounding rules is to decimal places. And it makes sense to get a negative number because look at the side. If this is 0, the mean is 1, the standard deviation is 0, we're right in the middle. Well, everything over here is negative, everything over there is positive. So our Z critical equals negative 2.05. All right, let's calculate the test statistic here. All right, let's write down the formula first of all to recall it. P with a hat minus P from the population divided by the square root of PQ divided by N. So let's put numbers. This is ours. This is the proportion from our sample, which is 0.592. 0.592 minus P, which is the population proportion, the one that is claimed, which is 0.64. All right. Then what else we do? What else we do? Let's see. Divide by PQ, which is 0.64 times 0.36, and divide by the sample size, which is 125. Using the graphing calculator, I get negative 1.12. All right, let's look at the number negative 1.12. Let's see what is going to happen here. If we go to our graph, is the number negative 1.12 smaller than negative 2.05 or greater than negative 2.05? Well, in this case, it's a number that is greater than, and look, it's falling in the unshaded region. This is statistic. All right. So hey, we failed to reject the null hypothesis. But hey, what we did the sample here. Come on. I mean, well, the global claim is at less than 64%. Yes, and we sample 125 people, and 74 of them, 74 out of the 125 people said, well, we don't want, we 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 like this president, you know. We're giving a positive approval to the president. Well, yes, that's unfortunately not enough evidence. Even though, yes, this number, 0.592, yeah, that's less than 64. No, so that's not enough. All right. So what are we going to say here? We fail to reject the null hypothesis. There is not enough evidence to support it. Well, what is going on here? I mean, we got numbers. Apparently we got compelling numbers that, in a way, support us to support our claim. But what could have gone wrong? Maybe there was an error in the sampling. You know, maybe the sample size must have been large, maybe larger than 125 people. I mean, if you think about it, well, we're talking about the President of the United States. Come on, only if you are serving only 125 people from the entire country, well, maybe it's not maybe it's not the right sample size. You know, maybe that's a source of error. You know, so maybe we need a way larger size and get better numbers. That's for sure. I can assure you that if we increase the size of this, well, our numbers are going to change. Unfortunately for this case, yes, despite our data here, despite our statistical calculation, I mean, we're not doing anything illegal. We are using the correct data, the correct distribution. Well, in this case, using our standard values, well, this is unfortunately not enough evidence to support the claim. So we need to conduct the experiment again. Maybe change the sample size, maybe obtain more people, maybe, you know, if we want, why not? A sample of 125 people, but maybe get less people in this case, because in this case we want a claim that is less than 64. Maybe we should get, I don't know, 31, and this p hat is gonna get way smaller, enough so that when we do this difference here, we get a number way smaller than our critical value. You know, well, so maybe we need to redesign the experiment and gather new data. You know, replace these two numbers with something else. Okay, so now let's do it using the second method. So again, this was method 1, using the test statistic. Now let's do it using the test, you know, the p-value, method 2. All right, so for method 2, I'm gonna go normal CDF of, well, in this case, be careful, because we are gonna go and find the area under the curve. You know, essentially we're finding the area under the curve from negative infinity, or from negative big, to negative 1.12. So in other words, this is our lower and this is our upper. All right, so let's see. Let's put the numbers. So negative big to negative 0.12, and again the calculator by default puts this 0 and this 1, which again we don't need it, but I'm gonna write this, you know, just so we are congruent with what we have on the graphing calculator. So I'm gonna go second distor for distribution, normal CDF. So in this case I need a negative big, you know, negative big. Oh, I'm running out of battery here. Hopefully it doesn't let me down on the next example. I'm gonna need it. And negative, oops, no, not the subtraction one, but the actual negative 1.12. Boom, paste, enter, I get 1.31, okay? 0.131. So I'm going to write P, which is the p-value that we obtain, and I'm going to compare it with alpha, which is the significance level. What did I get for P? I got 0.131. And alpha, which is the significance level, what was it? Wasn't it 0.02? Okay, so let's put this together. And what are we going to get? In this case, our p-value is way bigger than our significance level, you know? So this means essentially our experiment sucked, right? Look at the probability, it's really big in comparison with the precision. So significance level. Significance level, it's another way to say precision. The smaller the alpha, the finer the precision, the finer our experiment will be, you know? But in this case, look at this number. Well, I got a P kind of big, it's really big, you know? Well, this is not precise. This is not significant. This is so slopey, you know? So if the p-values essentially compare these two areas. So this purple area is our rejection area. So this is how much area or how much likelihood for the event to occur with a maximum of negative 2.05 as our cutoff value, if you will. But in this case, well, when we put our data, well, we get an area that is way bigger. So no, this area is going larger than our permitted. So this sucks. This is not good evidence. So that means, well, we didn't do the experiment carefully. We didn't take the sample accordingly. We didn't take the sample large enough. Or when or even if the sample size was good, well, in this case it's a good sample size. Why not? However, we needed the success, you know, the success to be a different number in order for this. So for this reason, we failed to reject the null hypothesis. And let's look at our third example here. Well, so let's see. A researcher claims that the proportion of US households that watch the Super Bowl on television is not 40%. Oh, where have you seen this? Is not before. Is not. Remember, what is that going to tell us? Finally, a two-tailed test. And that's what we're going to do here. Okay, in a random sample, 72 out of 140 households had watched the most recent Super Bowl. Test the claim at an alpha equals 0.05 significance level. Again, blah, 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 yada, yada, yada. Z-score to the critical Z-score and p-value with the level of significance. Okay, same song. Same saying here. All right. So, number one, population. We don't know and we don't care. Okay? But we still need to state that we don't know and we don't care. P and Q, the probability of success for the population, and its complement, well, in this case, 40%, that's 0.40 and 0.60. All right. What are we going to do? Well, take a sample. And, well, in this case, n equals 140, x equals 72, because that's the successes that actually watch the Super Bowl, on television. Okay, because there's people who watch the Super Bowl maybe on their phones, or maybe they go to a bar, but not on television at home. That's our claim in here. That's what we wanted to test in this case. So p hat, which is the quotient between x and n, that's going to be 72 over 140, which equals 0.514. Okay, that's kind of slopey here. Let me fix that. Okay, 14, not 12, 14. All right, so let's see. The quantity, or the part of the statement that I highlighted, is the one that is going to give us the alternative hypothesis. Let's state it. The Okay, so the alternative of hypothesis is to claim that the proportion that blah blah blah, the Super Bowl ultimately is not 0.40. Okay, for the null hypothesis, aka the whole, it's going to be the logical opposite of this statement right here, which in this case is p equals 0.40. All right, so let's get the work done. Okay, this alpha equals 0.05. That's the level of significance. Okay, so I'm going to write this alpha equals 0.05. Because in this case we have a not equal. This test will be two-tailed. So in this case, these two tails right here are going to be split in two. All right. But how is that going to be in terms of our alpha? Remember confidence intervals? Well, half of it to one side, the other half to the other side. That means alpha over 2 equals 0.025. Alpha over 2 equals 0.025. We split it in two. So if this 0.05 is a significance level, that means that's 5% significance. So the unshaded region will be 95%. Okay. So that means in this case, any value within this region fail to reject the null hypothesis. Otherwise, if it falls somewhere here, reject the null hypothesis. Or somewhere here, reject the null hypothesis. Okay, let's see. Let's get calculations done. How about that? So in this case, we're going to do inverse norm to find z critical. In this case, we're going to find two z criticals. One for the negative side, the other one for the positive side. How are we going to do that? Well, again, in norm. Z critical, that's in norm of 0.025. Okay, I'm gonna do it. I mean, I could give you the right answer, but why not? Ooh, don't die on me. Well, I have the answers anyway. Second, this in norm, area 0.025, 0.1 doesn't matter. Keep them or erase them, doesn't matter. Negative 1.95. Well, we round that to now 1.96. Alright, so this is going to be, well, actually negative. We got a negative number, but in this case we don't have to bother and calculate the other one. You know, why not? Because in this case we can take advantage of the symmetry of the Gaussian curve here and just put 1.96. All right, so that's what we're going to do. So we're gonna do the process that you have hopefully you're already used to the calculation, same formula, same data here. Well, different numbers, but same kind of data. If we get a C statistic that falls in here, well, we will lose the argument and we fail to reject the null hypothesis. Otherwise, if we fall in either of these two regions, well, then we win the argument. Then we reject the null hypothesis. So let's go ahead and do that. So Z equals P hat. Again, let's write down the formula. Divided by PQ over N. Let's write numbers. P hat, we got actually 0.514 minus 0.4. Divide that by the square root of the product PQ, which is 0.40, 0.60, over N, which is the sample size of 140. Using a calculator, I get 2.75. Okay. This time I will let you verify using the calculator. All right. So let's see. 2.75, where is this number going to be? Whew, look at this. 2.75 is a number larger than 1.96, which is the cutoff value for rejection. So it's going to be here. Very nice. What is our conclusion? Our conclusion here, we reject the null hypothesis. There is enough evidence to support it. All right. Now, before conducting the p-value method, well, this is the cutoff for this area right here. Because our statistic probability here, because our statistic area is smaller than the standard area, well, this means that we did a good job. Okay, now let's do the test. Let's see, P will be equals to normal CDF of, well, in this case, we go from 275 to huge, big. Okay, in this case, big. That's a lower, upper, and that's what we are going to put in our graphing calculator. 2.75 to big. So here in paper, I'm writing the big, right? And I'm going to have the 0 and the 1 again. And let's put it on the calculator. So, okay, yes, I know. Second quit. Second dister, normal CDF, That's 2.75, and big, really big, to ensure all the area is there. Paste and enter. I get 0.029. Really small number. Do you see the precision here? We got a really low p-value. That means we did a good job. That means this experiment didn't suck like the one we did before. Remember, really big probability. The area was actually bigger than the one from the standard value. So in this case, this sucked. In this case, it didn't. We did a good job here. But still, let's establish the inequality. So 0.0029, and alpha, which in this case is 0.05. Well, clearly this is less than or equal. Less than or equal. What do we know about that? Well, less than or equal, reject null hypothesis, which is actually what we got as our conclusion, didn't we? So we're good here. We're good here. All right? And this is a good place to quit. I will see you on the next video.